Alrighty, we're ready to get started. Our next talk is Red Teaming macOS Environments with Hermes the Swift Messenger. Our speaker is Justin. Our speaker is Justin Bowie. Justin Bowie is a Red Teamer at Zoom and was previously a Red Team consultant at SpectreOps. He's passionate about all things security and helping organizations improve their security posture. All right, take it away.
Cool. All right, cool, that's working. All right, just resetting my timer. All right, hello everybody. My name is Justin Bowie, and today I'll be talking about red teaming macOS environments with Hermes the Swift Messenger. So, small introduction on who I am. Like I said, my name is Justin Bowie. I go by the handle of @SlyDog. You can find me using that handle on things like Twitter, GitHub, or Medium. I'm currently a red teamer at Zoom, where I lead red team operations, purple team assessments, and perform research and development. Prior to Zoom, I was a red team consultant at SpectreOps, basically doing red team work there, and then also teaching the red team operations training. It should go without saying, but views and research presented are all my own. When I'm not messing with computers, I'm usually out skateboarding with friends and trying to learn a new trick. So here's a quick summary of what we'll be talking about today. First, we'll talk about the Swift programming language, how it works, and examples of post-exploitation tooling. Next, we'll introduce the Mythic framework. We'll talk about how it can be used in red team operations. After, we'll discuss the Hermes payload and how it hooks into the Mythic framework. We'll dive into development of the agent as well as functionality. And lastly, to round things out, we'll look into Apple's Endpoint Security Framework, or ESF, and how it can be used to detect different TTPs implemented within Hermes. So in this first section, we'll be talking about everything Swift. What is Swift, pros and cons as a post-exploitation language, and some examples of current Swift tooling. Swift is a high-level programming language that was developed by Apple. Swift 1.0 was released in 2014 and initially only supported macOS. As of Swift 5.3, cross-platform support was enabled for macOS, Windows, as well as Linux. Swift was designed to be safer, faster, and more optimized than its predecessor, Objective-C. Swift leverages the Objective-C runtime library under the hood. And this is particularly great for attackers because within a single Swift program, we can call C, C++, and Objective-C code. So if we need lower level functionality, we can access it through these bridging headers. I'll mostly be talking about Swift for macOS, but you can also write iOS and tvOS applications for Swift, or iOS and tvOS malware for Swift. So let's go through an example of compiling and executing Swift. If you take a look at the image, you'll see that we have BSidesSF.Swift, and the contents of that file are just a simple print statement saying, hello BSidesSF. Now, what happens if we pass this source code file to the Swift binary? So here we run Swift BSidesSF.Swift. The Swift binary is going to compile and execute this code in memory. And so you'll see that we're presented with hello BSidesSF to the terminal. Alternatively, if we want to compile this code into an executable format, we can use the Swift compiler or the Swift C binary. Using the Swift C binary, we can compile it, and then if we pass in the TAC-O flag, we can specify the output file name. And so in this case, it's going to be a BSidesSF, and it's going to be a Mako binary. We're going to flip the executable bit on that using chmod, and then kick it off on the terminal using /BSidesSF. And you see again, we're presented with hello BSidesSF to the terminal. Alternatively, Swift can be compiled using Xcode, which will basically call the Swift compiler under the hood. It should be noted that the Swift compiler is not installed by default. So if you attempt to call Swift or the Swift compiler when it's not installed, the user is going to be prompted to install command line tools, and this could blow your red team operation. While the compiler is not installed, the Swift libraries are installed as of macOS Mojave 10.14.4. These are runtime support libraries that exist on modern versions of macOS. Since they exist on disk, Swift applications no longer need to package them within them. So the size of the binary is smaller as a result of this. And so this is another plus for attackers. Here are some different languages for macOS post-exploitation. Notably, I'm missing languages such as C, C++, Objective-C, and Rust. I list out some pros and cons, but these are all fairly high level, so definitely take them with a grain of salt. I kind of pick and chose the ones that made the most sense to me. The first language I want to talk about is JXA, or JavaScript for Automation. JXA, with JXA, you can leverage it using a lol bin for execution. A lol bin is a living off the land binary, so a native binary on disk that you can use to execute code, perform malicious actions, post-exploitation, things like that. In this case, that binary is OSIS script. Additionally, with the JXA language, if you couldn't do something in pure JXA, you could likely do it using Objective-C. JXA exposes an Objective-C bridge, which allows you to call Objective-C API calls. And so anything you can do in JXA, you could probably do in Objective-C. Some notable cons for JXA are that it's single-threaded. So if you're trying to run something like multi-threaded or run multiple jobs concurrently with JXA, that wouldn't really be possible. Perhaps the biggest con of all is that development of the JXA language has been completely abandoned by the Apple team. It's pretty much like this no man's land language, currently exists. We don't know how long it'll exist for, but abuse it while you can. Some examples of JXA tooling include AppFell, a JXA agent for the Mythic framework, SwiftBelt JXA, some situational awareness for macOS written in JXA, and Persistent JXA, a collection of macOS persistence techniques written in JXA. The next language I want to talk about is Python. Python also leverages a lol bin for execution in the form of Python and Python 3. Some notable cons for Python are that Apple has publicly stated that scripting languages are going to be deprecated and removed in future versions of macOS, and they specifically called out Python in this case. Another con for Python is that it's a bit more heavily signatured by macOS defensive products such as Xprotect and malware removal tool. And this is because Python has traditionally been used in macOS malware and macOS intrusions, and so some of those rats have been signatured. Some examples of Python tooling include Medusa, a Python agent for the Mythic framework, Empire, a command and control server. This command and control server had a macOS agent, also written in Python. And then Chainbreaker, a script that you can interact with the macOS keychain from Python. The last language I want to talk about is Golang. Now, Golang is a fantastic language. You can write something once and then cross-compile it to many different operating systems, so like Windows, Linux, macOS. You can also very easily integrate Objective-C, C, and C++ code, so you can very easily integrate and interact with all the different macOS APIs. One of the notable cons for Golang is generally the binaries that you compile are a bit larger in size. And some examples of Golang post-exploitation tooling include Poseidon, the Golang agent for the Mythic framework, and Sliver, a command and control server and agent written in Golang. So you might ask the question, why would you use Swift for post-exploitation? Well, one, Swift, like most modern-day languages, has the ability to perform multi-threading, so you can run multiple jobs concurrently. Additionally, with Swift, you have very easy access to all of the different macOS APIs. So Cocoa, Foundation, AppKit, OSISKit, all very easy to use and integrate with. In my opinion, Swift is easier to develop than Objective-C and JXA. And I think this has to do with the fact that it's kind of the modern day language being pushed by Apple. So there's lots of documentation, examples on Google, Stack Overflow, Apple forums, things like that. Now, while Swift is a higher level language that allows for rapid development, we also have the ability to call lower level languages and APIs. So you can call C, C++, and Objective-C using these bridging headers that I talked about. So when we need that lower level functionality, we can utilize it. Lastly, an app whitelisting bypass, or a living off the land binary situation exists. When the Swift compiler is installed, you can use the Swift binary to execute code. Unfortunately, the Swift compiler is not installed by default. And so we often have to resort to dropping unsigned binaries to disk, which may be a bit harder than landing a Python script or a JXA script, and then kicking that off with OSIS script or Python. Here are a couple different examples of Swift tooling for macOS. We have SwiftBelt. This is a variety of safety checks for situational awareness. We have MacShell Swift. This is like a Swift command and control server. Swift Attack. Think of this kind of like atomic red teaming for macOS. Swift Spy, a keylogger, clipboard monitor, and screenshotter. Swift Parse TCC, a TCC database parser. And then some defensive products. Venator Swift. This is a data gathering agent to aid hunting on macOS. And lastly, there's Crescendo, a real-time event viewer that hooks into Apple's endpoint security framework. Notably, in the final section of this presentation, we'll be using Crescendo to detect different TTPs within Hermes. So in this section, we're going to be talking about the Mythic framework. We're going to dive into what Mythic is, how it can be used in red teams, its architecture, and then current Mythic implants targeting macOS. From the GitHub, this is a pretty good summary of Mythic. Mythic is a cross-platform post-exploit red teaming framework built with Python 3, Docker, Docker Compose, and a web browser UI. It's designed to provide a collaborative and user-friendly interface for operators, managers, and reporting throughout red teaming. In a nutshell, Mythic is a command control server that has lots of neat features, like a web UI, user access control, and a reporting. It does a really good job of centralizing all actions performed during a red team operation. It's open source at github.com/itsafeature/mythic, and there's documentation for developers and users at docs.mythicc2.net. Mythic is an extremely modular and customizable framework. It allows the implant developer full control over how their implant interacts with the Mythic framework. It does this by using Docker to separate out all of its different components. The primary Mythic server, the database, the payloads, the C2 containers, the documentation containers are all separated out into different Docker containers. Perhaps my favorite feature of all is that operators can simply connect to Mythic using a web browser. There's no need to install some sort of heavyweight client application just to connect to your C2 server. So technically, you could own things from your phone and just manage it all from a mobile device. Let's take a look at how traffic flows in Mythic. In this example, we're going to go through what happens when me as an operator execute an ls command on the home directory and how that gets executed on the implant, and then how that information travels back to us. So in the left corner, you'll see the operator's browser. Here's where the operator interacts with Mythic. So here we're going to execute the ls command on the user's home directory. The Mythic server is going to receive that command and then pass that command and arguments to the payload container in the top right. That payload container is responsible for pre-processing of the command and arguments. So it's going to clean up things like spaces. It's going to make sure that that command and arguments, by the time it reaches the implant doesn't have to do any additional work. And so this saves the amount of kind of code that you have to write in your implant. Once that command and arguments have been cleaned up, those are stored on the Mythic server. Now, if you look at the bottom right, we have the agent calling back. This is the computer that we've compromised. This agent calling back is going to send an HTTP request to the HTTP C2 container. The HTTP C2 container is going to parse the agent message from the HTTP request and then pass that agent message to the Mythic server. The Mythic server is going to respond with the command and arguments. So it's going to respond with that ls command on the user's home directory. Once the agent receives that command, it's going to execute that ls on the user's home directory and then pass that the data that it gets back to the Mythic server. So all of the files and folders on the home directory, the names, size, etc., are being passed to the Mythic server. Once the Mythic server receives that information, it renders that in the operator's browser, and that's kind of how end-to-end an operator issues a command. It gets cleaned up, gets sent down to the agent, and then the output is rendered in the operator's browser. Now let's talk about existing Mythic payloads that can be used to target macOS. It should be noted that the following payloads all use the Objective-C API calls to interact with macOS. The first one I want to talk about is the appfel agent. Appfel is the JXA agent for the Mythic framework. Appfel is great for initial access because it supports a download cradle, where you can download and execute JXA in memory using that OSA script binary. If you come from a Windows background, think of this like a PowerShell one-liner. You can pull down a malicious PowerShell script and execute it in memory. This is the same thing on macOS. The next one I want to talk about is Poseidon. Poseidon is the Golang agent for the Mythic framework. Poseidon is a bit larger in size, but more fully featured. It includes things like SOX proxying, as well as multi-threading, so you can proxy in your own tools if you need to. This makes it great for a second stage payload after you've gotten initial access with something like appfel. The last one I want to talk about is Medusa, the Python agent. Medusa also leverages a lol bin for execution in the form of Python and Python 3. One particular cool thing about Medusa is you can send down a small Medusa agent with only the load command. And then you can load all of your agent modules on the fly. So you can send down this very small payload and then load in all of your agent modules later on. And this makes it a bit harder to fingerprint. Another neat feature is you can run third-party Python scripts as well as execute Python code dynamically, all in memory. This is really just a brief summary of all of these payloads, and I'm really not doing them any justice, so I highly recommend you go out and try them for yourselves. As you may have guessed, Hermes is a Swift payload for the Mythic framework. In this section, I'll be going over the development of Hermes, and in a follow-up section, we'll dive into functionality. So what is Hermes? Hermes is a Mythic payload targeting macOS written in Swift 5. It's been tested on Big Sur as well as Monterey, And Hermes implements an encrypted key exchange for secure communications. And what this means is that each implant goes through this key exchange to securely generate a unique session key to encrypt all future agent traffic. Hermes includes various post-exploitation modules that include situational awareness, upload-download, execution, as well as job control. Before I dive into Hermes development, I want to talk about my motivation for writing Hermes. I find that writing implants is a straightforward and fun way to learn operating system internals, as well as pick up a new programming language. You can start small and write things like ls, print working directory, who am I, and then eventually move on to implement more complex things, such as encryption, command and control over HTTP requests, and a job control manager. Previously, I'd written a command and control server and agent called SkateRat and SkatePark. SkateRat was the implant portion and SkatePark was the server side. And I quickly realized that I hated writing the server component and I hated writing the front end component. With Mythic, I only had to write the part that interested me, the implant side. And so I highly encourage, if you want to dive into Mythic, definitely do and write your own implant. I want to start off by saying that cross-compiling for macOS is a pain. My goal was to compile Swift code to a macOS executable from a Linux container. And the reason for this is that since Mythic uses containers under the hood, I wanted to make it as easy as possible for an end user to download Mythic, download Hermes, and then compile a payload directly from Mythic without any form of external build systems. The first project I took a look at was OS X Cross. Poseidon uses OS X Cross to cross-compile Golang to macOS, but unfortunately, a quick look at the README, I found that it doesn't support Swift, so this wouldn't be the answer for me. The next project I looked at was Docker OS X. This seemingly was the answer to my problems. Unfortunately, Docker OS X needs to be run on a macOS host, whereas most C2 servers traditionally run on Linux servers. The last solution I looked at was AWS Pipeline and GitHub Actions. I looked at the free tier and didn't really like that there was an upper limit on how much you could compile. I really wanted a free solution that kept the payload config under end user control. And what I mean by that is within Hermes, there's a file that defines various secrets, such as encryption keys, C2 callback domains, ports, and other agent-specific secrets. I wanted to keep that information out of third-party control if possible. After a bit of searching, I discovered the answer to all of my problems: Darling. Darling is a macOS emulation layer for Linux. It's free and open source. And then if you're not familiar with Wine, Wine lets you run Windows software on a Linux host. Darling does the exact same thing, but for macOS software. You could install software such as Xcode, command line tools, etc. And you could also compile and run programs. Compiling programs is really all I needed it for, so let's walk through an example of that. Here's an example of cross-compilation with Darling. First, we run the uname command to show that we're on a Linux host. Then we drop into a Darling shell using Darling shell. And then we run the uname command again, and it returns DARWIN. So we're on this kind of macOS emulated layer at this point. So now let's go through that process of compiling Swift code. So again, we have BSidesSF.Swift. It just says print hello BSidesSF 2022. We're going to compile that using the Swift compiler, so Swift C, and then we'll be output the BSidesSF executable. We're going to flip the executable bit on that using chmod, and then we're going to kick that off with /BSidesSF. And you'll see that we're presented with hello BSidesSF 2022. So at this point, we're able to compile Swift code to a macOS executable from a Linux server. In the previous example, I was testing Darling on a Linux server. My next goal was to get Darling working with Docker, since Mythic uses Docker for everything under the hood. And there were a couple tricks I had to do to get Darling and Docker to cooperate nicely. First, the Darling Linux kernel module must be installed on the host and loaded prior to the container start. And the reason for this is that the Darling kernel module is the core to Darling. It allows for features that would be otherwise difficult or impossible to do purely from user land. Next, the container must be run in privileged mode. And this will basically allow the container to access the underlying driver on the host. With these tricks, Swift code could be compiled with a Docker container on a Linux host. Previously, your first Hermes build took about 10 minutes because I had to install command line tools manually every time the container started. I did a little bit of extra work and was able to pre-install it within the container. So now you can build payloads within a minute. You can download Mythic, install Hermes, and then you'll have a payload running within a minute. Cross-compilation was honestly one of the hardest parts of this project. Once that was out of the way, it was just writing Swift code. In this section, I'll dive into Hermes functionality and some of the code behind it. As I mentioned earlier, Hermes implements an encrypted key exchange for secure communications. Each implant goes through a process that securely generates a unique session key to encrypt all future agent messages. If that session key is compromised for whatever reason, other implants are not affected. The encrypted key exchange grants us what's called forward secrecy. And this means that even if long-term secrets are compromised, such as a pre-shared key, the negotiated session keys will not be compromised. Let's kind of walk through what this process looks like. So starting from the top, Mythic and Hermes start with a pre-shared key. When you first execute Hermes, it's going to generate an RSA key pair in memory, so an RSA public key and an RSA private key. It's going to use that pre-shared key, encrypt the RSA public key, and send that up to the Mythic server. The Mythic server, of course, has the pre-shared key, so is able to decrypt that RSA public key. Mythic will then generate an AES session key. It encrypts this AES session key with that RSA public key that was received from Hermes. Hermes, of course, has the corresponding RSA private key and is able to decrypt that AES session key. And so now Hermes has the AES session key generated by Mythic. Hermes will then gather various basic system information, such as networking information, process lists, username, process ID, things like that, encrypt all of that system information with the AES session key, and send that up to the Mythic server. Mythic will confirm this check-in as a new callback, and then send back down an encrypted acknowledged message. Once Hermes receives this encrypted acknowledged message, Hermes will begin beaconing. So once Hermes is beaconing, let's talk about what happens when an operator issues a command to Hermes. Every command and parameter issued on the Mythic side turn into a Hermes job. Each job is executed in a separate thread. And then when we create this thread, we track the thread ID so that we can kill the job at any time. So any rogue jobs or long-running jobs that we don't want to run anymore, we can easily kill those. Since each job runs in a separate thread, Hermes supports long-running jobs and jobs that don't return output immediately. If you look at the image on the right side, you'll see the jobs command will return all the current jobs with their command and the parameters. You have job control using the job kill command, so you can kill any jobs that you don't want running anymore using job kill and just specifying the job ID. Hermes has the ability to download files from the target and upload files to the target. This is performed in 512 kilobyte chunks and occur within normal command and control traffic. The URL request structure defines the HTTP method, the headers, the URL, and the path. The URL session class is what is responsible for making the actual web request. For upload, the operator wants to upload a file to the target. In this case, Mythic is going to take the file size of the file you want to upload, determine how many chunks it'll take to send down to the target, and then start sending portions of that file down to the target. Hermes will incrementally create this file on target. So when it receives chunk 1, it's going to first create the file. When it receives chunk 2, it'll just keep adding data to this file. And so the benefit of this is that the entire file is never stored in implant memory all at once. So theoretically, you could upload arbitrarily large files to the target. Download works the inverse to upload. For download, we want to download a file from the target and transfer it to our command and control server. In that case, Hermes is going to take the file size and determining how many chunks it'll take to send up to the Mythic server. Hermes will then start reading chunks of that file and sending them up to the Mythic server. Once Mythic receives all of the chunks, the file is recreated on the server and made readily available for the operator to download. Upload and download can also be performed from Mythic's file browser, which I'll also be showing in a later slide. Of course, as with any implant, you have to be able to interact with the file system. Hermes implements all of this using the file manager class. So you have all of your classic file commands such as change directory, list contents of a directory, print working directory, making new directories, moving or copying files or directories, and then also removing files or directories. You can also perform file listings and file removals from the file browser, which I'll show. So here's an example of running the ls command on the user's home directory. You see the various data that's returned includes the size of the file or folder, the name of the file or folder, the owner, the group, the POSIX permissions, and then on the left side you'll see an actions button. If you click the actions button, you can issue further Hermes commands such as downloading that file or removing that file. Additionally, you can view extended attributes such as com.apple.quarantine from that view. So here's what the file browser looks like. On the left side, you see the various host names of hosts that have been compromised. If you expand the host names, you'll see all the files and folders that have already been enumerated, as denoted by the green check mark. The file browser is a nice way to kind of move around the operating system. As you click through folders, you can issue further ls commands and kind of enumerate those contents. You can even upload files directly to the folder from this view. On the right side, you have a bit more information about the file. You have the file, the size, when it was last modified, things like that. If you click the Actions button in that view, you can do things such as issue further ls commands, download the file, or even delete the file. One of my favorite features of Mythic's file browser is you can actually add a comment. And so if you discover a file with important credentials, or you know this file is important for whatever reason, you can make a comment. And so that when your team is browsing to this particular directory, they'll see your comment and kind of just like all that information is kind of all readily available and shared. So what would an agent be if you couldn't execute things on the target? Hermes implements this in two different ways. One, using the run command. The run command will execute a binary on disk with arguments. And it does this by using the process class to execute the binary, and then the pipe class to capture any output. If you look at the image on the right, we're running the ifconfig binary, so just printing out network information, and then passing in the EN9 network interface. And you can see that that output is returned properly. Next, Hermes has the shell command to basically execute a bash command with bin bash tac-c. This works extremely similar to the run command, but instead of passing in a particular binary, the binary we're passing in is bin bash, and then the arguments are tac-c, and then whatever the operator wants to execute with the shell command. This is particularly useful if you need input and output redirection. So if you look at the example on the right, we have shell ls applications, and then we're able to pipe that output to grep Slack, and then we return with slack.app. So here's kind of how the shell command works under the hood. First, we have that process object and that pipe object. And then you set up that process object by setting the executable URL. In this case, we're kicking off bin bash. And then for the arguments, we're passing in tac-c, and then all of the arguments that the user or the operator wants to execute using the shell command. We redirect standard output to our output pipe, and then we run that process. Once that process is run, the last command is what actually reads the data from the pipe, and then we take that data and send it back up to the command and control server. So binary and process execution is cool and all, but what's even cooler is executing JXA, or JavaScript for automation, in memory. This is achieved using the OSA script class. OSA, or OSA in OSA script, stands for Open Scripting Architecture. This includes languages such as JXA and AppleScript. You can execute both of these languages in memory. Hermes implements this three different ways. One is with the JXA command. The JXA command will basically execute any arbitrary JXA. And so if you look at the image, I pass in math.py, and it returns a couple digits of pi. More interestingly is the JXA import command. You can use the JXA import command to load JXA scripts into memory. And this works very similar to the upload command that we went over earlier, except instead of writing out the script to the target, we store it within implant memory for later use. Once that script is stored within implant memory, we can call various functionality within it using JXA call. This way, using JXA import and JXA call, you can load up lots of third-party tooling. And so if you look at the image on the right, I'm loading up Health Inspector, which is a kind of JXA tool, into memory. And then we're calling the allChecks function. And lots of macOS post-exploitation tooling is written in JXA, so this is very handy to have. Hermes has a few different ways to enumerate and interact with running processes. Using the ps command, you can gather a list of running processes by parsing the kinfoproc struct from the syscontrol routine. This will return all BSD processes, including Linux daemons. Next, we have the list apps command. Oh, this image totally got messed up. Sorry, I don't know when that happened. Next, we have the list apps command, and that will return all applications running within Carbon, Cocoa, or Classic environments. And so this is basically all applications that you see in your dock, things like Slack, Zoom, things like that. What got covered up here was the last command, which is kill. For kill, if you pass in a process ID, it'll basically kill that process using the kill system call. In the image below, you can see an example of the list apps output. You can see that we have the name, the bundle, the size, things like that. If you click actions, you can see additional information such as the full path to the binary. Additionally, there's a browser script that exists that will highlight the frontmost application. So if the user is currently using Zoom or Slack, that will be highlighted and presented to you. And that kind of gives you additional context on what the end user is doing on their day-to-day basis. So here's how the process browser looks like in Mythic. On the left side, you have the process tree with most things as a child of launchd. On the right side, you have a bit more detail on the different running processes. You have things like process ID, parent process ID, architecture, process name, and process owner. If you click actions on that right view, you can do things such as kill the process as well. An interesting feature that I haven't shown here is that you can actually issue a new process listing from this view, and you can actually diff between the old and new process listing to see old processes that have died and new processes that have started over time. And this just gives you additional context on, like what the operating system is doing over time. So Hermes also has the ability to take screenshots of what the end user is doing. It should be noted that this requires the screen recording permission within TCC. If you do not have this permission, the user may be prompted to allow your application permission, and this can potentially blow your operation. Or if they have denied it in the past, you will get a screenshot back, but it's going to be an empty desktop with no applications and no windows. Not very useful. Screenshot works using the Core Graphics API. It does this by performing a screen capture of all the different displays. First, you call cg-getActiveDisplayList. This will return the number of active displays. So if you have a laptop, that'll be 1. If you have a laptop and monitor, that'll be 2, so on and so forth. You pass in this number to cg-getActiveDisplayList again. This will return a list of active displays that you can actually iterate through. Once you have that list of active displays, you can loop through those displays and grab an image with cg-display-create-image. These images are sent up to the Mythic command and control server in normal C2 traffic, and then they're displayed to the operator. Screenshot is great because you can gather additional context on what the user might be doing on a day-to-day basis. Hermes also has a clipboard monitor to perform clipboard command to perform clipboard monitoring. And this works by monitoring the change count property within the NS-Pasteboard class. If that number increases, we know that clipboard ownership has changed and that something new has been copied to the clipboard and to retrieve it. Unfortunately, there's no clipboard event that we can kind of listen for, so we have to resort to this very primitive polling. It should be noted that root does not have access to the general pasteboard, and so if you've landed in a privileged context, you actually don't have the ability to access the system clipboard. Clipboard monitoring is particularly great for things like password managers, because if people are copying and pasting passwords from the password managers, you can easily nab them using this. It can net you credentials or just give you more context on what the end user is copying. So like maybe they're copying internal links, things like that. Hermes has lots of built-in situational awareness commands and safety checks for macOS. Most of these safety checks are inspired by Cedric Owens' awesome research, so definitely check him out if you get the chance. I've linked a lot of his work in the references. The first one I want to talk about is get execution context. This will read various environment variables to determine your execution context. And so reading environment variables, we're able to determine if we're running in a terminal context, if we were kicked off from an application bundle, or an installer package. The next situational awareness check I want to talk about is FDA check, or full disk access check. This will check if our current process has full disk access permissions, and there are two methods of doing this. The first is using the MD Query API. The MD Query API can be used to determine if the TCC database exists within the Spotlight database. Basically, if Spotlight has indexed the TCC DB, then we know we have full disk access permissions. The second method is the file handle method. In this case, Hermes will attempt to open up a file handle to the user's TCC database. If that file handle is returned properly, that means we have full disk access permissions. If it does not, then we do not. The next command I want to talk about is TCC folder checker. This uses the MD Query APIs to check for access to TCC protected folders such as desktop, documents, and downloads. Very similarly to the FDA check, if we identify the desktop, documents, and downloads folder within that MD Query API, then that means we have access to those TCC protected folders. The last kind of check we have is the accessibility check. This uses the AXIsProcessTrusted to check for accessibility permissions. Big shout out to Dazzle Spy Malware, which kind of introduced me to this technique, and my coworker, Chris Ross, who basically reverse engineered that malware and identified this safety check. And so I was able to add it to Hermes. And the last thing is being able to enumerate the TCC database. You can do this using list TCC. List TCC will list out all the entries in a specified TCC database. This requires full disk access permissions to read from that SQLite database. The TCC database schema changes over time, and so this command currently supports Big Sur and above, so Big Sur and Monterey. Here I want to talk about how Hermes can enumerate PLIST files. If you come from a Windows background, PLIST files on macOS are very similar to the Windows registry. They serve as configuration files for applications as well as parts of the operating system. They can be of the format XML, JSON, or binary. Using the property list serialization class, we're able to parse any type of plist. In the image below, I show the universal access auth warning plist. And this is a particularly interesting plist because it shows us any application that has caused a prompt before. And so this may give us insight into what applications are used by the user that may have triggered a TCC prompt and potentially have interesting TCC permissions. And this is a method of kind of potentially enumerating TCC permissions without triggering any prompts. Hermes has the ability to enumerate and interact with all the environment variables. You can list out environment variables using the env command. And how this works is by reading the environment field within the process info class. You can also set and unset environment variables using setenv and unsetenv. These just use the DARWIN standard library. It should be noted that if you try to set an environment variable that currently exists, you will overwrite it. So just something to be careful of. In this last section, I want to talk about how we can detect some of the different TTPs we went over within Hermes using Apple's endpoint security framework. Here we're going to talk about Apple's endpoint security framework. If you're familiar with Windows, think of event tracing for Windows. As of Big Sur, Apple pushed all third-party developers out of the kernel, and so this included security products. And so this put security products and security researchers on the same playing field. We had access to the same data. Using ESF, you can hook into various events, such as process events, file events, as well as memory events. There are several free and open source tools that leverage Apple's ESF. Some of them include Appmon by Xorier, Crescendo by Superhacker Steve, and File and Process Monitor by Patrick Wardle. We'll be using Crescendo as well as File Monitor to kind of identify malicious activity. So here's an example of how we can detect shell commands with Hermes. So on the left side, we're running shell ls tac liah from the Mythic server. On the endpoint side, we see that a process exec event fires within Crescendo. You have various information such as the timestamp that occurred, the arguments that occurred, the process that performed the process exec, the username, process ID, parent process ID, things like that that can aid your investigation. And so this is one way of kind of detecting shell commands run through an implant. So before I talk about how we can detect launch agents, I just want to give a quick primer on what launch agents are on macOS. Launch agents are a background process that launches whenever a user logs in. Think of this like the startup folder on Windows. Launch agents are defined with a property list file or a plist file in the following locations: library launch agents, users, username, library launch agents, and system library launch agents. The third one is protected by SIP, or System Integrity Protection, so it's less of a concern most of the time. An attacker won't be able to write to that file, or that directory, sorry. Launch agents are great because attackers can utilize this for persistence. So this is an example of what a malicious launch agent might look like. This is in the form of XML. You'll see that there's this program arguments key, and then the program arguments key has the value /temp/Hermes. So if we place this plist file into one of those directories from the previous slide, every time the user logs in, the program /temp/Hermes will be executed. So how can we potentially detect this? So on the left side, we're uploading a malicious launch agent to target. We're uploading that com.hermes.plist to one of the launch agent directories. On the right side, this file create event occurs within Crescendo. The file create event tracks information such as the process that performed the file create, the timestamp, process ID, parent process ID, and that various information. And so if we kind of look for file creation events within these directories, we can potentially detect any launch agents that are created. Now, here I want to go over how we can detect the FDA check command, or the full disk access check command. On the left side, we're running the FDA check command with the file handle, technique. And remember, the file handle technique opens up a file handle to the user's TCC database. On the right side, we use file monitor to detect this activity. Basically, this ES event type notify open event occurs every time file handles are opened. So if we look for these file handles being opened, we can potentially detect this type of post-exploitation. It records various information such as the process that performed that file handle open, the timestamp, and various information like that. That pretty much wraps up the defensive portion. I just want to go, last slide is kind of just how to install Hermes. If you want to go out and install Hermes, first you'll have to install Mythic. Mythic is the command and control server from GitHub. On Ubuntu 20.10, you're going to install the Darling kernel module, which is how we perform that cross-compilation from GitHub as well. And then you're going to load up that kernel module using modprobe darling-mock. Once that kernel module is loaded, you can install Hermes from GitHub using the Mythic CLI, and this is included in the Mythic repo. And then from the Mythic CLI, you can also start up the payload container. And if all goes well, in your Mythic instance, you'll be able to go to the payload section and see Hermes with a little green kind of box or circle, showing that the Docker container is up and running successfully. Here are kind of some various references that I referred to in my presentation. Give it time for people to screenshot or whatever. And that's pretty much it. Just want to give a big shout out to Cody Thomas, or the developer of Mythic. It's a feature who helped me endlessly when I ran into bugs during development on the agent side as well as the server side. Big thanks to my old coworker Brian for the awesome Tony Hawk Pro Skater 2 Photoshop that I basically use everywhere. Thank you BSidesSF for allowing me to share my work, and then thank you for coming and listening. Really appreciate your time.
All right, we have a bunch of time for questions. So if you have any questions, raise your hand, or you can submit on slido.com, hashtag BSidesSF 2022. Any questions out there?
Question in the back?
You were describing the exploit to a C2 server. What
Yep.
does that network traffic look like? And because I just didn't see it mentioned in your detection method, it seems like that would be one option for a soft to identify potentially malicious outbound traffic.
Yeah, so the current kind of C2 traffic that Hermes implements is all using HTTP or HTTPS traffic. And so depending on how the attacker masks that traffic, potentially using domain fronting or like cooking legitimate domains, it would look like that. I guess potentially you could detect anomalies if you have really good network data on like this domain has never been reached out to before, et cetera, and potentially like catch those anomalies.
And then how do those file create events differ from standard functionality within the macOS environment?
Yeah, that's a great question. Oftentimes, these detections can be more difficult to scale up because these events are happening very frequently. You'll have to combine the file create events with other kind of detection logic to really nail in on this activity. Thank you.
Any other questions?
One more.
Sure.
So is it a 360 flip or is it a tray flip?
That's a great question. I call it a tray flip. I love it.
Nice.
Thank you. Thanks again, everyone.